Fluid rheology at the microscale explores how fluids flow and deform under applied forces in confined, small-scale environments, such as microfluidic devices, biological systems, or nanoscale channels. At these scales, the behavior of fluids differs significantly from their behavior at the macroscale because molecular interactions, surface tension, and boundary effects dominate over bulk properties like inertia. For instance, viscosity, elasticity, and non-Newtonian behavior, e.g., shear thinning or shear thickening, are influenced by the geometry of confinement and interactions with channel walls. Techniques like passive microrheology use tracer particles embedded in the fluid to track their Brownian motion, providing insights into the fluid's local viscoelastic properties. Active microrheology applies controlled forces to the particles to probe fluid resistance, enabling precise measurements of flow characteristics. This understanding is critical for designing and optimizing applications like LabOnAChip systems, medical diagnostics, and microfabricated sensors. A compelling example is blood flow in microcapillaries, a biological system where microscale rheology plays a vital role. Blood, a complex fluid, exhibits non-Newtonian properties. It becomes less viscous as the shear rate increases, known as shear thinning. This property ensures efficient oxygen and nutrient transport in tiny capillaries. To study this behavior, researchers replicate capillary networks in microfluidic devices. These devices allow them to measure flow properties, such as how viscosity changes with red blood cell concentration, or how blood clots affect flow dynamics. Such studies are essential for diagnosing and treating conditions like thrombosis or anemia, where altered blood rheology disrupts normal flow. Imagine honey flowing through a straw. At a large scale, honey appears thick and flows relatively predictably. However, if you were to squeeze honey through a very fine needle, its behavior changes dramatically. Surface forces, friction with the needle walls, and small-scale stickiness significantly impact its flow. Similarly, at the microscale, fluid behaviors are dominated by molecular interactions and confinement effects. Microrheology acts like a magnifying glass, allowing scientists to observe and manipulate these small-scale fluid behaviors for specific purposes. By mastering microscale fluid rheology, scientists can design systems with precise control over fluid behaviors, advancing fields like biomedical engineering, material science, and nanotechnology, where efficiency and precision are paramount.